Divya, you can start recording. Good morning. This is Somak Raychaudhury, and this is my second lecture on this special topic of galaxies and their groups and clusters. In all, this is the sixth lecture in this series that I'm giving, the first four being at the very beginning of this course, where we talked about very introductory topics in astrophysics. This has been now almost 2/3 of the way through the end of the course, and I'm happy that a lot of you are still attending and asking very insightful questions, showing that you are paying attention to what's going on, and we've covered a lot of ground. You will find many astrophysics courses that cover so much in their whole ambit. It shows that where I am, IUCAA has a bunch of people in their faculty who actually cover almost all of astrophysics, and they're willing to share their knowledge with you. In the last lecture, which was on Monday morning, we what happened? We talked about how galaxies don't live, quote unquote, live in the universe. Galaxies don't inhabit the universe alone. They mostly are congregated in small groups, and slowly these groups build up into clusters. As groups merge, galaxies merge into bigger galaxies, groups merge into bigger groups, which we call clusters. And as we shall see today towards the end, clusters are also connected in bigger structures, which we call superclusters. And so this is a simulation which I showed last time, which essentially shows how dark matter in the universe is distributed. And you can see that it's very filamentary, it's not very uniform. And they are these filaments, which are almost like cosmic highways along which galaxies travel, have these crossroads, which are clusters. That's where the galaxies congregate, but there are also small structures, which are the groups. And I also said that we live in one of these small groups called the local group, which I showed last time is a very typical system. Most of the galaxies in the universe are in groups that are similar, very small, 2 or 3 galaxies, along with lots of tiny galaxies, which are our satellites. And in this particular case, Andromeda and our galaxy, the Milky Way, are bound together because they're falling towards each other, even though the universe as a whole is expanding. We ask the question here, how on cluster scales, the actually thing that holds these clusters together is dark matter. And we look at the evidence of dark matter today in a limited way. And so these are our nearest clusters. This is the nearest cluster, the Virgo cluster. It's about 15 megaparsecs away. By this time, you understand the scales and the units that we use. The Coma cluster, which is a slightly more richer cluster, thousands of galaxies, dominated again by a big elliptical, is about 100 megaparsecs away. And this was this. And we also talked about how these clusters are made up of galaxies. They're intergalactic stars. There's hot and cold gas. We looked at how we can detect the cold gas with radio astronomy last time, and then there's dark matter. We talked about the cosmic baryon budget, yes, in the last lecture, where we looked at the baryons, which are in the form of neutral gas, molecular gas, hot gas, etc. Now, looking at the dark matter, you know, in previous lectures that dark matter in the 1950s, 1960s became a fashionable subject, even though I talked about Zwicky measuring dark matter in clusters of galaxies in the 1930s. Not many people paid attention to him. We came back because of this remarkable woman, Vera Rubin, who recently passed away. Vera Rubin in her master's thesis, had done this remarkable job of looking at the um, the galaxies, nearby spiral galaxies. I showed you this picture in which I showed that there is a lot of this neutral atomic hydrogen, which can be traced out far beyond where the stars are. Here in these pictures, the negative, the optical pictures are the negative, and here, so the galaxy image that you see is the optical picture, and the contours are of neutral hydrogen measured from the 21 centimeter line by radio telescopes. You can see you can go very far away from even the stars. You can detect them. And what Vera Rubin did was she traced these the neutral hydrogen in the galaxies, in nearby spiral galaxies, out to a very large distance, far beyond, as you can see here. You would find the optical stars, the stars that you see in the galaxy. And she found, for example, in galaxies like these, that if you measure the velocity, the radial velocity of that gas from the Doppler shift of the 21 centimeter line, it of course is not 21 centimeters, it shifts because if you're looking at a galaxy that is side on like this, then as it's rotating, one bit of it would go far away from us and the other bit will come towards us. And so the line will shift and you can measure the velocity. And as you go from the center of the galaxy out towards the periphery of the galaxy, this velocity rises and then flattens out. But if you look at the solar system, what happens is that the velocity falls off from the center of the solar system, the sun, and the planets are moving slower and slower and slower. And that is because most of the mass of the sun, the solar system, is in the sun. And as you go away from the center of where the mass is, and if you're outside the main concentration of mass, then you have much lower velocities. And from Kepler's laws, you essentially know this. And this is called Keplerian fall off, and the velocity falls off as 1 over r to the power half. You can do that calculation yourself if you haven't done it. If you have a point object in the middle, but galaxies are not point objects. And so in the galaxy, as you go away, and if you just look at the stars and you thought that's where all the mass is, and you did this calculation, this is the velocity versus radius, the rotation curve that you'd expect to fall off. And it doesn't. Vera Rubin found that it actually goes up and then flattens off, even outside the galaxy where there are no stars. And this was a result that when she submitted to the astronomical journal, was rejected. And even though he got her master's degree for a thesis, people didn't believe in her, partly because she was a young woman. In those days, women were not in the forefront of science in the 1950s, early 60s. And also this was a very, very unusual result, and people did not remember that Zwicky had already talked about this kind of missing matter in galaxies, outside galaxies, in between clusters, between the galaxies in the 1930s. It was when a much more senior male astronomer went and repeated her experiment later on. The same result was found. And of course, now it is a very, very well-established result. It's a shame that she did not get the Nobel Prize. It was one of the major, major results in physics of the 20th century. But Vera became very famous in her lifetime, and this became a big industry of measuring the rotation curves of galaxies and measuring the masses of the actual masses. And thus we know that the galaxies themselves are very huge. They have dark matter, and the bits you see in the middle in the stars are much smaller than the actual extent of the galaxies. And of course, I have done a lot of these myself, and so have many of my colleagues, trying to measure the actual masses of galaxies in various ways. And this is the kind of result that you get. But I go back to then where I ended the last lecture and talked about how 30 years before Vera Rubin, Zwicky had done a similar calculation, but not with rotating systems, But with systems that are in thermal equilibrium, which are clusters of galaxies with lots of galaxies in them, the coma cluster, which I showed you before, I showed you how he used the virial theorem, in which the virial theorem in a system in equilibrium has the right-hand side equal to 0. And that means that twice the total time average kinetic energy plus the potential energy would be equal to 0. And to calculate the potential and the kinetic energy, what you have to do is you have to take a half mv squared for all the galaxies that you see, or many of the galaxies that you see, and then how to do that? What you do is, because you can measure the radial velocity of a galaxy from its Doppler shift, and then in a system that is far away from you, which is spherical, and galaxies are going around in all directions, you assume that if you measure the radial direction, that is actually there are three such directions. There are two directions perpendicular to that radial direction. And just as you do the same in the kinetic theory of gases, if you remember, if you try and find out the velocity dispersion of a system and relate it to its temperature, here too, what you do is you take the 1 degree of freedom, which is the velocity in the radial direction, and you know that there are three such directions. You can't measure transverse velocities on the sky, and so you multiply the kinetic energy for 1 degree of freedom by 3, right? You remember you do the same thing in kinetic theory, and so this is the 3/2 m sigma squared. And sigma is the velocity dispersion in the radial direction. If you know statistics tells you that the dispersion is the deviations from the mean. So the mean of the cluster would be the mean velocity of recession of the cluster away from you, right? Because the universe is expanding, and then within that cluster, all these galaxies are moving everywhere. And so the deviation of the velocity of each galaxy from the mean of the system, and you take each of those that you've measured, and Zwicky did that, square them, add them, that is your sigma squared. That's the dispersion. The square root of that quantity is the standard deviation, if you've learned in statistics. So this is your, and so 3/2 of that, that's your T, which is the kinetic energy. And the potential energy, I showed you how, and you must have done this in class as well. The potential energy of a spherical system, you can get from -3/5 gm squared over r, where m is the mass of the full cluster. If you take the two together and plug it in here, you'll get an equation. This just shows you how to calculate the velocity dispersion. And so, for example, if you measure the radius of the cluster to be, say, a couple of megaparsecs, which he did on the sky, and he looked at the angle between the farthest galaxy from the center and the center of the cluster, and from an estimated distance, he could find the actual size of the cluster. And then he, of course, his scales were wrong. I mean, in the 1930s, he did not really know the distance to the coma cluster very accurately, but still, he did this exercise, and we can repeat the exercise now with the values we know now. And so this is, I framed it that way to help you, do this yourself. And then if you have the cluster like that, and the one-dimensional velocity dispersion, sigma is it's a square of that quantity. That's the standard deviation. Then if you use 2t plus v equals 0, v is -3/5 gm squared over r, t is 3 times half mv squared or half m sigma squared. Then you get the mass of within a distance r from the center to be 5r times sigma r squared, sigma being the one-dimensional velocity dispersion. You can go back and look at this. I'm going to post these slides on our wiki, and you can look at it and do this yourself, but try and do this yourself. You remember in my introductory lectures, I used units that make things, such calculations easy. You can, of course, put in centimeters and meters and I know kilograms and stuff like that in here and calculate this. You know that if you put g equals 1 and the units of speed to be 1 kilometer per second and the distance to be 1 kiloparsec and the time to be 10 to the 9 years, the unit of mass turns out to be 2.3 times 10 to the 5 solar masses. And if you do all that and you plug in all these numbers, etc., you get something like 10 to the 15 solar masses, 3.5 times 10 to the 15. So Zwicky found that the mass of the Coma cluster is 10 to the 15 times the mass of the sun. If he then took all the galaxies that he saw and scaled them by some kind of their light, their luminosity by some kind of a standard conversion from our sun, we know, for example, the mass of the sun, the light given by the sun. Then you take all the light that he got from the galaxies in the Coma cluster and he scaled it by that factor. He found that it was 500 times short of the mass that he was measuring. And he said, then there must be a lot of matter in between these galaxies. And this he called dark matter, which again, people forgot. And Peter Rubin came back in the 1960s and found that, of course, in the outskirts of galaxies, you have this evidence of matter being there. Professor Varun Sahani will come back to this next week when he talks about dark matter and dark energy and review how, what we now know, review other evidences of dark matter. So there are many other ways of measuring this matter in the universe, and I will talk about two more ways of measuring mass on the larger scales from clusters of galaxies that show you some of the properties of these clusters. So one was the way by just the motion of the galaxies in the cluster, which Zwicky did. There are problems with this method. You have to assume equilibrium, and clusters are often not in equilibrium because they, as I said, things are merging all the time in the universe. And so clusters are merging into bigger clusters, groups are merging into, forming clusters. And so that right-hand side in that Virial theorem cannot be assumed to be 0 for most of these systems. Then there are other problems as well. And that is to do with, actually you see very, very little in the galaxies themselves. And the galaxies, if you use those as points, as test particles, as your which sample the background mass, then you have to ask the question whether they're biased test particles or not. And so it's a good way of doing this exercise by doing it in different ways. And there are more direct ways of doing this. So I'll talk about some of those now. So one of the things that I alluded to last time as well is that clusters of galaxies have all these things that are there. There are, of course, the galaxies, and then there's the cold gas, which is outside the galaxies. But I also talked about, when I talked about the baryon budget, I said that the predominant component in the baryons is the hot gas in the cluster. And the hot gas is about 10 to the power 7 degrees hot. And as a result, it emits in the X-rays. And there are many others in this course who have talked about X-ray measurements, X-ray clusters, measurements of X-ray AGN, X-ray detection of black holes from binaries and X-rays. Professor Ranjiv Mishra has talked about it. Professor Gulab Devangan is talking about it. So I'm not going to go into the basics of X-ray astronomy. Suffice to say that you can take these now, some of the most wonderful space telescopes. You have to go to space to get X-ray images because our atmosphere absorbs the X-rays that are emitted by celestial objects. And the satellites like Chandra, NASA's Chandra, XMM, Newton from Europe, and of course our own AstroSat, which ISRO launched 5 years ago. they have taken some exquisite images of these clusters, and you can see this. I mean, on the left and on the right, you see this here, the purple that you see as the diffuse hot gas, which is glowing in X-rays due to thermal Bremsstrahlung emitted from it, something that Professor Dipankar Bhattacharya told you about in the very first week, one of the radiation processes from celestial objects. And so thermal Bremsstrahlung is causing this, and the thermal nature of that Bremsstrahlung means that there is some relation between the kind of Planck temperature, which is the 10 to the power 7 degrees, and the radiation that you see from it. On the right is only the X-rays from another cluster, and you can see this hot gas glowing. Just to show you a direct comparison from the same cluster, this is on the same scale. On the left, an optical image of a cluster I studied quite well, Abell 3528, and you can see an optical picture, and you can see the galaxies. On the right, the same galaxies have been replaced by ellipses, black ellipses, and you see the hot gas. Now, from the left picture, you would never know that there are two clusters in there, right? You can see lots of galaxies, but you can see that galaxy is that galaxy, that galaxy is that galaxy, and in between the stuff that's there, and this is all false color. The color that is being put there is essentially an indication of the temperature of the gas, and so you can see that it's just full of this hot gas. And by looking at the X-ray picture, we can actually figure out the shape of the gravitational potential around these. There's no way the galaxies themselves can tell us that. So this is why we have to put all these various observations from various parts of the electromagnetic spectrum together, and we can find out that this is. So what I was trying to say there is that this hot gas is not dark matter. Because dark matter, remember, is non-baryonic. This hot gas is the baryons that sits in the non-baryonic potential well, and as a result of the gravitational potential energy of the dark matter potential, this dark matter gets hot. So just like you did a calculation for how much dark matter there can be in clusters by looking at the virial estimate of the cluster, you can do the same by looking at the clusters themselves. By the X-ray emission, you can measure the mass. And the way this is done, and this was done from the 80s when the first observations of these clusters were made, is that one, you can assume again spherical symmetry, not a very good assumption, but that's how you start. You can assume hydrostatic equilibrium between the gas in between the galaxies and the dark matter. That is a better assumption than assuming that the galaxies themselves are in equilibrium with the dark matter, because the diffuse gas will settle into the gravitational potential of the dark matter that is the big halo that is holding together the cluster. And if you do that, and this again, you can look at in any books of high energy astrophysics, X-ray astronomy, and I'll give you references in the slides I post. What you do is you look at the pressure gradient in hydrostatic equilibrium. This is exactly the same calculation that was made when you looked at the pressure equilibrium and the hydrostatic equilibrium in a star to find out the temperature of a star. So you've come across this equation before, earlier on in Professor Srianand's lecture, for example. And so if you look at the hot gas that you just saw, and if you assume that it has pressure at every point from this spherically symmetric system as a function of radius, and you know that you can relate that to g times the rho, and the hot gas, the density of hot gas, and the mass within a certain radius r from this equation. And you assume the ideal gas law, the perfect gas law, which gives you the pressure in terms of rho and a lot of other things, and temperature. This is just your ideal gas law from thermodynamics. And you put that together, and so what happens is that if you take that and just rewrite it in this form, you get something like that. And organizing this is from this paper by Fabricant et al., where they did it. Of course, this is now in most textbooks. And you make some adjustment for the abundance of the gas. The gas is mostly hydrogen, but it's not quite hydrogen. It's hydrogen plus some higher elements, which is a very small fraction of it, but it will add to the mean molecular mass or atomic mass or whatever of the plasma. Remember, this is the gas that is the hot gas is at 10 to the power 7 degrees. Is a plasma. It is not neutral gas or molecular gas or even ionized gas. It's a plasma, and this plasma is emitting X-rays. And by measuring the temperature of this gas, by fitting various models, etc., to it, by measuring the density of this gas as a function of radius. So you measure the density profile, you measure the temperature profile. You do this by fitting models is very standard way of doing this. You can find the mass as a function of radius of this system. And then up to a certain radius, you can measure the total mass. So this is an independent way of measuring mass of a cluster, not the dynamical way that I showed you that Zwicky did, right? And you do this for something like, say, the Coma cluster, you get essentially the same result. Sorry, I don't know why I have all this. Right. So you essentially get the same result, a few times 10 to the 15 solar masses. Now, a final way of measuring masses is something which you've already come across through the lectures of Professor Surud Mori and Anuprita Mori, and that is gravitational lensing. So you know that from Einstein's theory of general relativity, we know that matter causes space to curve, space-time itself, and then and the more the matter in any place, the more the curvature of space. And so, for example, if you have a dark blob in front of, say, this picture of a mountain, then you would find that because space-time itself is warped and the light that's coming from this distant source to you has to travel along curved paths, the images are distorted. And from this you've seen before in the lectures of Surud Mori. If you have a galaxy in the background and you are here, and you have a cluster of galaxies in the middle, which I just showed you consists of dark matter halo with lots of galaxies moving in between in there. And so these rays of light that comes from galaxies in the background to you, they will come along these curved trajectories to you, and as a result, they will give images of these galaxies that you see in the background to be distorted, just like you saw the distorted picture of the mountain, and then from that you can measure the amount of matter that is causing this distortion. So this is a much more direct way of measuring matter. There is no assumption of equilibrium, dynamical equilibrium, hydrostatic equilibrium here. This is simple ray tracing for Maths principle, geometrical optics, and the knowledge of how much a light ray bends due to matter. And that's a simple formula that comes from general relativity that you can use. And the assumptions that are made here are different. Then it's not that this is assumption free. For example, one assumption that is made here is that this bending of light happens over a very short distance, and this distance is much smaller than this whole thing, which is a good assumption. And so there's what is known as the impact approximation that's made, and also it's made is that the width of this system is very small compared to this whole expanse. So that's kind of a thin the galaxy cluster, which is causing the bending is thin compared to this whole distance, which is also a very good assumption. And so once this is set up as a lens, so this is a gravitational lens. This means that the ray of light that's coming from the distant galaxy is bent by this gravitational lens as it comes to you. It helps you model these clusters. These are spectacular pictures taken by the Hubble Space Telescope of clusters of galaxies, and you see this, that what you see there are these galaxies which are in the cluster itself. You don't see the dark matter, but through these galaxies, these are the galaxies in the cluster that are the spiral galaxy, these elliptical galaxies, etc. This is April 2018, and what you don't see the dark matter in between the galaxies, but what you see are these distorted images of these galaxies that are in the background. So these, if you measure the redshifts, which we have, of course, every single galaxy in this particular picture has had its redshift measured, so we know how far away they are, and we know that this cluster is in the foreground at a redshift of about 0.2, and these galaxies are much further away, redshift 1 or so, or 0.8, 0.7, something like that. And you can see multiple images. So this galaxy and that galaxy are the same galaxy, and you can see them in two different places because you're looking at the ray that's coming through the cluster to you, and you see then the same this galaxy image. If you follow your line of sight follows back the ray, you'd see them in different places. So these are wonderful pictures taken with exquisite resolution from the Hubble Space Telescope. And you can, for example, see here that there are multiple images of the same galaxy forming this arc. And you can see the same galaxy replicated in different parts over a circle, showing that there's a lot of dark matter in there. And you can actually measure the amount of dark matter in this particular galaxy cluster because of that. Of course, the galaxies themselves will also cause the deviation of the light. And so you have to, if you're doing, I've had these students work on mass modeling of galaxy clusters from gravitational lensing. And if you want to do that, you take into account the deviation of the light due to the dark matter of the galaxy cluster as a whole, plus you have to add in the deviation of light due to the individual galaxies themselves in the cluster, as well as on the way and things like that. And you do all that, and you add all of that in forming in reconstructing the image of the background galaxy. And from that modeling, you can find out how much dark matter there is in the cluster. And so this is a beautiful way of measuring. It's a very hard way of doing it. It requires amazing observations and amazing modeling techniques. A lot of physics goes into this, a lot of painstaking corrections for knowing how much blurring there can be due to the instruments themselves, which can also cause various of these distortions. You have to know your instrument perfectly. You have to know the setup perfectly. It's a lot of very hard work that can be done. And so you get these massive so now, if you put all this together, then you get this amazing picture of what is in a cluster. This is what we've been talking about. So here are all these things put together. So there are these are pictures of 6 different clusters, and there are 3 things that have been put together just to show you how the different components of the cluster are superposed on each other, right? So the pictures themselves that you see, and you can hear probably the rain from outside my window. Pune is going through a storm right now. And So you see these pictures of the Hubble Space Telescope pictures of these clusters in which on the black background, you see the galaxies, which are the specks of light. These are all the galaxies. The purple in this picture, these pictures are just the X-rays taken from the Chandra satellite. So these are smooth gas in between the galaxies. So those are the purple bits. The blue bits, is very interesting, is the dark matter. And that is modeled from the gravitational lensing that I just told you about. So, and that is that. So the dark matter from lensing, this is superposed on the galaxies. You can see that in this particular case, the dark matter follows where the galaxies are. But in this particular case, it is not true. It is not true. It is not true, right? This is where the gas is. This is where the matter is. This is where the stars are. And you put all these together and you come up with an amazing picture of a galaxy cluster. And so it just shows how complex these systems are, how complex the universe is. And if you want to find out more about what these exotic objects are, this is where thousands of galaxies live. These are the oldest systems of galaxies that there are. You know that you have to study them from various different ways in order to build up this story about each of these clusters. And this is why the astronomer is a detective. He actually, the astronomer gathers clues from different observations, X-ray observations, lensing observations, optical observations, etc., and puts this together. A good example of this is the bullet cluster. A bullet cluster became very famous in the last 10, 15 years, 20 years, when we saw in the same kind of color scheme. You can see that the mass of the dark matter inferred from the gravitational lensing is very different from where the X-ray gas is. And here we know that what's happened is that two clusters have collided and the dark matter is displaced from the hot gas in between the galaxies in the cluster because it is going through a collision. And what happens is that because the dark matter doesn't interact with each other, it's non-baryonic, it can go through, whereas the hot gas, which consists of baryons, stick together and they don't go through very fast through each other. So two clusters have collided, and it is caused temporarily, but in cosmic history, temporarily means billions of years. They have been separated. And so this is a spectacular example of how through gravitational lensing and through the X-ray studies, you can come up with very different pictures of the cluster. And you can see then the Zwicky type of argument, where you assume dynamical equilibrium, apply the Virial theorem, and find the mass of the cluster, the total mass of the cluster. We've come such a long way from it in 100 years. That is not the kind of it gives you a basic idea. It helps you say that there is dark matter in the universe. But if you want to do detailed study of how all this is distributed, a lot more physics and a lot more observations are needed. So I wanted to end, the last topic I wanted to cover was that in general, we assume in the cosmological principle, the universe is homogeneous and isotropic. And we discussed this in some of the questions in the last lecture. And but now I've told you that the universe is clumpy on even tens of megaparsec scales. So the question is, at what scale is the universe not clumpy? It is homogeneous. Isotropic, okay, that's a different thing. If you heard, some of you might have heard the colloquium given at IUCAA by Professor Shubhi Sharkar last week, in which he talked about how people have started to question whether the universe is has large-scale flows in the universe and things like that. So these are so the questions that are being asked is, on what scale, on how large can these structures be before you can say the universe is nice and smooth and homogeneous, right? The universe is few gigaparsecs in size, and here I'm talking of tens of megaparsecs. So at 100 megaparsec scales, is the universe homogeneous? And the answer is no. We now are finding bigger and bigger and bigger surveys, which we, in the 1980s, the CFA survey showed us, and you'll see a few of these wedge plots. The wedge plots are like this. So here, if you look at the plot that you see here, here we are here, and this distance, this axis, it's a polar plot. Along this radial distance is distance away from us. This is actually redshift, and so redshift is proportional to distance. And on the theta, or on the azimuthal axis, is actually the right ascension or longitude on the sky. And so this is a slice of galaxy. Each point is a galaxy. So galaxies in the direction of the Coma cluster was plotted in the 1980s, and people realized that when people first started realizing that there are like filamentary structures, and the structure in the center here is actually the Coma cluster. It is actually a 1 point, but in redshift space, it is smeared out in the radial direction because the galaxies are moving in various with various velocities within it, right? But you can also see in a transverse direction there are large structures, and even in the 1980s, people realized that this large structure is tens of megaparsecs large. My own work in the 1990s showed that if you take this, the Shapley supercluster, for example, that I worked on, which consists of about 35 clusters of galaxies. Here's only one. You can see the same kind of structure in much larger scales. So this is from my PhD thesis in the late 80s. And if you compare this particular the Coma cluster, this is much smaller than this huge thing. And so this particular structure consists of 35 different clusters, and they form a larger scale. And this whole scale is going now up to 50, 60, 70 megaparsecs. So even on this scale, the universe is not homogeneous. That is the interesting bit here. How large can these bound structures get? Are these bound structures, can they be 50 megaparsecs large? Remember, a cluster is 2 or 3 megaparsecs in size. And then you have these superclusters, clusters of clusters, like the ones I'm showing you, can be as large as 50, 60, or even 100 megaparsecs. So we are looking at, this is this question I cannot give you the answer to, how large is the largest structure in the universe? The more we look, the more we make these three-dimensional maps of the universe, the more we find ways of measuring accurate distances to galaxies. We find larger and larger clusters. Here are some of the superclusters, clusters of clusters that I have worked on. I've had PhD students who've done their PhD thesis on actually mapping out these large structures quite a lot. Here's the Shapley, as I told you, which I worked on in the 1990s. More recently, I've had students work on other superclusters. Here's another one, Pisces Cetus, in which there are about 20 clusters or so. And you can see in the same way, this is distance away from us. That is one direction, angular direction on the sky, and it's a wedge. It's a wedge, and each point, each red point in here is one galaxy, and you can see this filamentary cosmic web-like structure. And so the cosmic web itself, as you can see, are little filaments connecting the individual clusters. The clusters are marked here with these squares. These clusters, and so the whole system forms a supercluster. So we call these superclusters, and the largest of these are yet to come. Here's a very good example of a recent supercluster called the Sloan Great Wall. And you can see these are very, very large structures. Still not the whole universe. We are not saying that the universe itself is not homogeneous on the largest scales, which is a basic assumption that people use in cosmology. You saw how Dr. Paranjape and Dr. Kandaswamy Subramaniam showed you how we use this assumption of homogeneity to then go and find out more about the structure of the universe. That itself, I don't think, has been challenged yet. But on the question is, on what scales is the universe homogeneous? And it looks like even on 100 megaparsec scales, the universe is not completely homogeneous. And as you go out, it starts looking homogeneous. This is another big chunk of that millennium simulation that I started off with in the last lecture. I showed you a very small part of that part, which I took about 100 megaparsec. But if you zoom out, you can see this kind of a foam-like or spider web-like structure. And the idea is that as you go zoom out more and more and more, this will look more and more homogeneous. But the larger structures will still be big. I will finish. So this is some kind of a cartoon, which I took this from Wikipedia. If you look up supercluster in Wikipedia, somebody's made this kind of a cartoon in which you can see that we are in the middle. These are our nearest superclusters. So that's the Shapley supercluster, that's the Hercules supercluster, Pisces Cetus is somewhere here, and things like that. So all of these, that's what I showed you. I showed you Pisces Cetus. Many of these I have worked on, and this is going out to maybe up to about a few hundreds of megaparsecs away from us. Recently, we are our own galaxy is part of what is known as the IUCAA supercluster, which Brent Tully has worked on, and you can look it up in Google and find out more about it. Our local group is embedded in what is known as the Virgo system, and this is part of this IUCAA supercluster. Recently, you would have heard that people at IUCAA, led by Joydeep Bagchi, and various others, Shishir Sankhayan and Pratik Davade and myself, we were all involved in finding another of these very, very large systems, which we call the Saraswati supercluster, which got a lot of attention in the press a few years ago, 2-3 years ago. It's a 200 megaparsec long system, same kind of thing where you're looking at distance away from us, and this is right ascension on the sky, and this doesn't look very impressive here, but it's at a much further distance than the Shapley supercluster. The Shapley supercluster would be at about this distance, whereas here this is much further away, and so much further away means much smaller on the sky, and it's 200 megaparsecs, and it has 40 massive clusters in it, and its mass could be more than 10 to the power 16, many times 10 to the power 16 times the mass of the sun. You remember the Coma cluster itself is 10 to the power 15 times the mass of the sun. Here you have 40 clusters, and so the size of this supercluster would be much larger. So we are just looking at bigger and bigger systems. We got a lot of press from it, as you can see. Chief ministers of states congratulated us, and the science minister congratulated us for finding these supercluster. And I would end with saying that even though scientists like us do not dwell too much on getting press coverage, we are really happy when Amitabh Bachchan acknowledges us. So this was the final question in Kaun Banega Crorepati, which was about 3 years ago. And this man who was answering this question actually did not know the answer to this. So you know this now. And you know that attending an astrophysics course can make you a crorepati if you are at the right place at the right time. I'll stop here and I'll take questions. So let me go to I will ask people to raise their hand, use the raise hand option, and I will from your list I will unmute you, okay, and you can ask questions. So I'll wait for a few minutes, and so you can go ahead. Vishal, I'll unmute you. Please go ahead and ask your question.
Good morning, sir.
Yeah.
Yeah, sir. Sun, our Earth rotates with respect to Sun.
Yes.
Then our galaxy, every galaxy will rotates with respect to which object?
A good question. Very good question. The Earth goes around the Sun. The Sun goes in the galaxy. If you attended my first lecture, I asked you to calculate how the Sun rotates in the galaxy. The galaxy then falls towards Andromeda and is in the local group. The local group is falling towards the Virgo cluster along one of these filaments on the cosmic web. The Virgo cluster is moving towards the center of the Laniakea supercluster, and the Laniakea supercluster is moving towards the Shapley supercluster, and things like that. So there's a whole hierarchy of motions. And so the question is there a reference frame in the universe? Yes, of course there is. That is the universe itself. And the universe itself is, the reference frame in the universe is the cosmic microwave background. You've heard about this in other lectures. The cosmic microwave background is the radiation that is left over from the initial part of the initial Big Bang. And so this has never moved from the universe. This fills the universe, the cosmic microwave background. So, and we can detect it in the microwaves. So since we know the cosmic microwave background and we can detect it, we can measure the velocities of everything with respect to the cosmic microwave background, which is the rest frame of the universe. I hope that that answers your question. Can I go to, I'm just looking at questions in which Arjun Da, where are you? Can you ask your question? You sent, okay, I can't. So I'll just go, Junik Shengupta, can I ask you? Yes, go ahead, ask your question.
Hello, sir, good morning. Sir,
how would you pronounce your name?
Sir, it's like Junik, Junik.
Okay, good, okay, go ahead.
Okay. Sir, my question is that, likewise, we know that apart from the baryonic matter in the galaxies, dark matter also contributes to the mass of the galaxies. And this point is now yet confirmed that dark matter contributes to a higher amount to the mass of the galaxies as compared to this baryonic matter. So my point is that, is this part yet confirmed? Like, how come dark matter contributes to this higher mass? Like what is the reason behind dark matter's so large amount of mass contributing towards?
I don't understand. I mean, you measure it, so you know that it's there. I have no idea, you know, where it came from, if that's what you're asking. What we can do is, what I'm saying is, the way I structured this lecture was how observers, observational astronomers or observational cosmologists, are trying to figure out what these things are made of. We know that galaxies themselves are made up of stars and baryonic matter, and in the form of gas and dust. And they're embedded in larger systems that are dark matter, which are not baryonic. It's non-baryonic. And then the galaxies themselves are contained in these large halos of dark matter, which is non-baryonic, same thing. And they're moving in there, right? So, and we can find out on the galaxy scales, the amount of matter in the dark matter is maybe about 5-10 times the amount of matter that is in the baryons. But in the cluster scale, the amount of dark matter is hundreds of times, maybe up to 500 times, I don't know, of the matter that is in the baryonic scale. So there is much more dark matter filling the clusters in between the galaxies. That's what I wanted to say. Now, so it means that it's the dark matter that holds all the baryons together. It's the dark matter that forms the halos the large clouds of matter in which galaxies form, and galaxies themselves have their own little dark matter halo, but the stars are formed in the galaxies themselves. Okay, so this is kind of the hierarchy of formational structure of the universe. Is dark matter that sets it. Our handicap is that we don't see the dark matter, right? And so we see only the light spots of light that are the stars. And now we've begun to see the X-ray hot gas. We've begun to see some of the cold gas in radio. And so from these clues, we're trying to piece together the unseen universe, which is essentially dark matter. Okay, right. Let's go to the next one, Shayuk Patro. Shayuk, can you ask your question? Shayuk, I've unmuted you.
I guess he won't able to.
Okay, so let's go to Gitanjali Sethi. Gitanjali, can you ask your question?
Yes, sir.
Yes, go ahead.
Sir, I was just wanting to ask that isn't it strange that whatever scale you look at dark matter, whether it is at galaxy scale or cluster scale, the behavior of dark matter remains the same. In the sense, it seems to remain same. Isn't it something that isn't it something that's astonishing?
It's interesting, I would say. I won't call it strange because what happens is I won't call it strange because it might be the same thing, right? The dark matter. Imagine the universe made up of one kind of matter. These are supersymmetric particles, maybe GeV particles or something like that, which is the background matter of the universe, in which sets the gravitational profile of the universe. It tells you in these places there's a lot of gravitation because of so much matter, and that's where the baryons, which is the minority of the universe, hard to think of ourselves as minority, but we are the minority, the things we are made up of the minority, and they congregate in these places, which sets the gravitational profile of the universe. And because of this hierarchy of structure, of certain structures formed first, and Professor Subramaniam has told you how we characterize this kind of thing. The hierarchy of structures, certain structures form first, maybe galaxy scale structures form first, then they break up into stars and globular clusters and things like that. And on the larger scales, galaxies then congregate to form larger and larger systems. We expect the underlying particles that form the dark matter to behave the same, right? And on the larger scales, there's only one kind of force that's important, and that is the gravitational force. Because on these large scales, you do not have electromagnetism, you do not have the strong or weak force, right? And so the universe is simple to some extent on these large scales, because we have to only deal with the gravitational force. So it is not surprising to me. It is interesting, but it's not surprising to me that it behaves in the same way. And it is frustrating because we want to detect these dark matter particles and to find out how they behave. We want to ask questions, but these things don't interact with the baryons. And so our detectors are built out of baryons, and so we can't catch them. And so we can only feel their presence by indirect means, and that is through their gravitation, how they compel us to move, how they set the gravitational potentials in which we inhabit. And that is what's the interesting bit. And so our detective work has to be much, much, much stronger in order to figure out the nature of dark matter. And we are not there yet. And that's the challenge in astronomy, astrophysics, physics itself. It's one of the biggest challenges in physics. If tomorrow we understood everything of the universe, we'll all lose our jobs, right? So here you are. Here are opportunities for you. Sweta Ghosh next. I've unmuted you. Sweta, go ahead.
Hello, sir.
Yes.
My question is, that is there no dark matter outside the blue spot which was taken by Hubble telescope?
What blue spot? What blue spot are you talking about?
Which was taken by Hubble telescope using gravitational lensing.
I don't understand what you're talking about. So I showed you these pictures of clusters of galaxies, which are taken by the Hubble Space Telescope, the black and these galaxies, right? And the
Yes, sir.
gravitational lensing. This is called weak lensing, and this you heard from Dr. Surud More before. How we reconstruct the mass that's underlying the underlying dark matter by looking at weak lensing of gravitational lensing, and we infer that that's the mass, right? So we know that there is dark matter here and here and here. Yeah. So that's the blue bit. Blue is of course false color. Mass is not blue. So are you asking whether there is mass here? Is
Yes,
that
sir.
yes? So no, of course there's matter everywhere. There must be matter. The universe is made up of dark matter. I showed you the pictures of like we believe that something like this, for example. This is a simulation, but this is a simulation of dark matter, right? What you're seeing here is that cluster might be one of these systems, and we are measuring the center of it where the dark matter concentration is much. But you can see there's matter everywhere. There are some places there is no matter, and these are called voids. But they are also localized. But there's matter almost everywhere. We cannot detect, even through gravitational lensing, we cannot detect low levels of matter. We can only detect the very high levels. So we are looking at only the peaks of the distribution of matter through gravitational lensing. And as our measurements get better and better and better, we are going to go down and look at the lower and lower and lower density places. So starting from here, we will try and map. We haven't been able to map these kinds of systems, all the filaments, through gravitational lensing yet. We've only seen the top bits, right? And that's because of the nature of the limitation of our weak lensing measurements, which I'm not going to go into, but I think Surud did. And but we also know that there are these voids in there in which there is no matter. But dark matter is everywhere. It is spread in various concentrations, and the galaxies are in the places where there is most of the dark matter. And there are no galaxies, for example, in these voids. But there is matter everywhere. Okay, I hope that answers your question. Let's go to Himadri Shaha. Himadri is next.
Hello, sir.
Yes, go ahead.
Sir, you have shown that using the temperature and the density profile, we can measure the mass of galaxies.
Yeah.
But sir, can we use the same method for measuring the mass of Milky Way, or is there any other method?
The Milky Way, the mass of the Milky Way, is hardest because we are inside it. So we can't even take a picture of the Milky Way, can we? So the Milky Way, so I can give you another course of 20 lectures on how to measure the mass of the Milky Way. There are many ways of doing it. But yes, finding the rotation curve. So we can find the rotation curve, which is the velocity as a function of radius within the Milky Way also. That has been done. And it's a much more difficult problem because we are inside it. And that gives you a measure. We can't do gravitational lensing of the Milky Way because we are inside it. There is no X-rays measured in the Milky Way, so we can't measure it that way. But we can now, if you were there in my first few talks, I talked about how Gaia, as a satellite, is now making a three-dimensional map of the Milky Way. We have measured the positions and velocities of about 1 billion stars, and this is being done now. And so once you have a three-dimensional map of the Milky Way in both position and velocities, you can make detailed dynamical maps of parts of the Milky Way, and you can measure the mass from the gravitational attraction inferred from the motions. And that is the best we can do right now, I think. There are many other ways of doing it, but that is, I think, the Gaia map of the Milky Way will give us the best, not just the whole mass, but the distribution of matter in the Milky Way. That's going on now. And again, people who will start doing their PhDs around now or in the next few years will be the first people who will do this. Shayuk Patro, I can see, has returned. If you can ask your question, go ahead now. Otherwise, I'll go to Yashwant. Yes.
Am I audible now, sir?
Yes, you are. Yeah, go ahead, Shayuk.
Good morning, sir.
Yes.
Sir, my question is, if the dark matter are non-baryons, so how do they interact with photons coming from a galaxy behind and creates gravity in case of gravitational lensing?
Understand. No, they don't interact. The photons are not interacting with the dark matter. What is the non-baryonic dark matter is doing? It has its gravitational field. And that gravitation of that dark matter is causing the space-time to bend. What the light does, the photon does, the photon, it just follows the shortest distance between 2 points in the universe, Fermat's principle. It just goes from one point to the other and it follows. And so if space is flat, it will go in a straight line. If space is curved, it will follow a curved route. It is not because it is being pulled by the dark matter. The dark matter, according to that's the basic difference between a Newtonian approach of gravitation, where gravitation means that it is a pull, as if there's an invisible string between two things, pull between two things. Einstein showed us that Newtonian approach that we learn in school is most of the physics using Newton's approach. But once it comes to understanding questions like yours, your question is very good in that sense, that once you start asking what makes light rays bend, Newton cannot give you an answer. Because in Newton's physics, light is massless, and so there cannot be a gravitational force on it. Your question is slightly different, which is also an interesting question, and that is how can a non-baryonic particle interact with a photon? Both of these are bypassed by Einstein's approach to gravitation. Einstein tells you that space-time is bent, and that's the geometry of space-time, and all light is doing is minding its own business, going along the curved geometry of space-time. I hope that answers your question. I'll take the last question from Jashwant Yadav, who has been raising his hand. I don't know whether anybody in YouTube has asked any question. Are there any questions from there? Otherwise, Yashwant, go ahead and ask your question, please.
Yeah, hi, thank you. So my question was that we have been discovering these large scale structures, like we have discovered Sloan Great Wall, then we have discovered this Saraswati supercluster and so on. So is there any, do you think, is there any limitation to the scales to which we will be able to measure the large scale structure if we scan the universe on large scales with powerful telescopes? Or do you think these structures are limited in numbers? Thank you.
I'm not an astrologer, so I cannot predict how my subject is going to go. But the only clue I have are from simulations like these. Okay, so these are realistic simulations in which you take billions of particles, put them in some kind of a realistic initial conditions of the universe that we get, which is consistent with what we measure from the cosmic microwave background. And we then let the universe evolve on a computer using gravitation between these particles. These take a huge amount of computing time, and people are doing more and more realistic simulations as our computing power grows. And it gives us pictures like this. And it tells us that there is structure on all scales. Here, hundreds of megaparsecs are scales like these, and you have big structures like that. And we are in real life, observationally, we are starting to discover these structures. right? And so that is reassuring that the simulations are doing something that are not what in the 1970s and 1980s people told us. The simulations showed us that that these structures can exist, and we've gone out with powerful telescopes and found them. Now, I asked you, I actually posed this question: how large can these structures get? And this is essentially what you're asking. And the answer is we don't know. It would be a big surprise if we find. It was a big surprise for us in the 1990s. I remember when I first discovered the Shapley supercluster in my PhD thesis, and I went around giving talks. Jim Peebles, who got the Nobel Prize last year, was in the audience in Princeton when I gave a talk there, and he said, "Absolute rubbish. I don't believe a word of what you're saying, because you cannot have something that is 50 megaparsecs large, because our cosmology doesn't predict it." Now, of course, I've talked with Jim Peebles since then till now for the last 30 years, and we know that as a community, our view has changed. Now Jim will look at these pictures and say, "How wonderful!" And so we are learning, as astronomy is an observationally driven subject. It is theoreticians can only do so much and predict how this will be, but then observations will come and completely overturn it. So as I said, I will be very surprised if we have structures that are 200, 300 megaparsecs large, because that will then start stretching our assumption of homogeneity in the universe, large-scale homogeneity. But if we do find it, we will have to live with it. Okay, that's a good note to end this lecture. Thank you very much for being so patient and listening to me. I'm clashing into the time allocated to the next lecturer, so I will